Alright folks, welcome back to another Math Notes. Today we're going to be talking about describing spread in data. There's a lot of new concepts in this Math Note, so you're probably going to want to pause periodically, take some notes, draw the figures, and you may need to even go do some Googling to look up some other stuff if you're still confused. Alright. So when we're talking about describing spread, what that means is if we have a bunch of data, let's say for example quiz scores, maybe we need to know more than just the class average. The class average is an example of the center of the data. That's the mean, median, and mode stuff that you guys have done before. So in addition to the center of the data, we're interested in how spread out the data is. So maybe we want to know like what the high score was, what the low score was, how many kids were close to the average or on one side of it or the other. So that's where we get into describing spread. So this first paragraph here, distribution of single variable data can be summarized by describing its center, shape, spread, and outliers. 3 ways to describe the spread are explained below. So the first thing we're going to look at is the range of the data. The range is the simplest measure of spread, and it's just the maximum minus the minimum. It's usually not a good way to describe the spread because it considers only the extreme values in the data rather than how the bulk of the data is spread out. But it is the simplest way. If I just look at the max score, let's say this was a 30-point quiz, I could say that one person got a 30, and that was the high, and that my lowest score was a 11. So the range of my data there is 30 minus 11, or 19. Another way to talk about spread is called the interquartile range, or the IQR. And there's a lot of stuff embedded in this concept of IQR. Let's look at this here first. So the variability or spread in the distribution can be numerically summarized with the interquartile range, or the IQR. The IQR is found by subtracting the first quartile from the third quartile. The IQR is the range of the middle half of the data. The IQR can represent the spread of any data distribution, even if the distribution is not symmetric or has outliers. So in the data set below or above, the IQR is Q3 minus Q1, which is 28 minus 19, or 9. Let's pause this for a second and talk about what the heck Q1 and Q3 are, and what the median is for that matter. So if you recall, the median is the middle of your data. So in this data we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 points. To find the middle of our data, I'm going to use this little equation that I've written off here to the side, which is the position equals the percentile times n plus 1. So the n is the number of data points, and the percentile for the middle would be the 50th percentile. So I'm going to say 0.5 times 13 plus 1. Well, 13 plus 1 is 14, times 0.5 would be 7, so that would be the 7th position. So 1, 2, 3, 4, 5, 6, 7. So our median value, and is in the 7th position, and is 25. Q1 is the first quartile, and a quartile, if you think about splitting things up into quarters, then as a percentile that would be the 25th percentile. So I'm going to use the same formula to find Q1, and actually let me put some numbers on. Let me put a little median position. Is going to be at 0.5 times 13 plus 1. Q1 is going to be at 0.25 times 13 plus 1. And so 0.25 times 13 plus 1 is 14 times 0.25. So let's pop up our calculator here. 14 times 0.25 equals 3.5. So that means that our first quartile is actually going to be at the 3.5 position. So if I go 1, 2, 3, it's going to be in between my third and fourth. So even though I have this written down here, a more accurate description of the Q1 would be the average of 15 and 19. Now, what they've actually done here in this example is they've just rounded that 3.5 position to 4, and they've said it's the fourth position, which is 19, which is a sort of simpler method for doing that, and I'll go ahead and use that here for this. So we're saying the fourth position is at 19. To find the Q3, the third quartile is going to be at the 75th percentile, so we say 0.75 times 14, or 13 plus 1. And we'll pop up our calculator, and we'll say 14 times 0.75, and we get 10.5. So again, we could either average the 10th and 11th place or just round that up to the 11th place. So let's see what we got here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And for some reason they've used 28. I don't love that. I would rather it be 28.5. But again, since this is already sort of worked out, we'll just use what they have bolded and say 28 minus 19, and we'll give ourselves an IQR of 9, which means that about half the class scored between a spread of 19 and 28. And we'll do an example with IQRs and whatnot on the next slide. Actually, before I move on, let's talk about a common way to represent these data. And that is a box and whisker plot. Up here at the top of this, I've got this little box and whisker plot set up. And if you line up the box and whisker plot with the data, you can get a sense of how these things work. To draw a box and whisker plot, you draw a number line first, and you put your leftmost line on the minimum value and your rightmost line on the maximum value, and then you put a line at Q1, Q3, and the median, which is also Q2. And you have a box that represents the spread of the data. So when we have our data lined up, you can kind of imagine just a box and whisker plot sitting right on top of that. I'll talk about that more in the next slide. So standard deviation. Either the interquartile range or standard deviation can be used to represent the spread if the data is symmetric and has no outliers. The population standard deviation is the square root of the average of the distances to the mean. So think about that. To find that, you need to find the mean, and then you need to subtract the individual data points from the mean, and then square those values. And then take the average of it and take the square root. So there are 13 values in the population, and the mean value is 22.77, which we had up here. Mean is 22.77. So we're going to start by subtracting each of these values from 22.7, or subtracting 22.77 from the values. So if we do 11 minus 22.77, we get a negative 11.77 that goes in here. The next the next value would be 13, so we do 13 minus 22.77, we get negative 9.77, and we do that for all the values, and we square the individual terms. And we get this number here, which is 500.3, and then we're going to take that number, divide it by the number of values. We have 13 values, and take the square root, and we get 6.2, which is the population standard deviation. Now, the nice part is that for the most part, we don't do this by hand. It's a button on your calculator. So if you have 1,000 data points, you're not sitting there entering each of these individually, squaring them, adding them up, dividing by the total, taking the square root. You just put all the data in a spreadsheet or in a calculator and have it spit it out for you. And there's also this thing called a sample standard deviation. Let's talk about that, because gathering data for the entire population is often impractical. Most of the data sets we analyze are samples. To calculate the sample standard deviation, divide by 1 less than the number of values in the data set. If the data set above is a sample from a larger population, then the sample standard deviation would be the 500.3 divided by 12 instead of 13, which would give you a slightly higher standard deviation. All right, let's talk about some box and whisker plots, why we would use them. I have a little example here. Here we're charting the temperature in Southampton weather station from 1950 to 1999. So we've got about 50 years worth of data there, and we're going to plot it all in one graph. Well, you're used to seeing a graph that might look like this red line that shows that the water temperature is higher in July, lower in January. That generally makes sense as long as you're in the northern hemisphere. And this maximum temperature, we're going to assume that's in Celsius and not just Fahrenheit. Otherwise, these would all be below freezing. So the nice part about this box and whisker plot is I'm looking at actually 50 years worth of data all in one place. And instead of just looking at the red line and going, oh, in July the water temperature is 21 degrees, I can see that in July, in the lowest year, the water temperature was actually only like 18 degrees. And in the highest year, it was like really 25, and there's even an outlier year where it was like 26 maybe. So I'm getting all of this data in one convenient graph that I would not be able to get otherwise. And it's a lot easier too than looking at, say, a spreadsheet or just a big table of data. It's a really convenient way to display a lot of data at once. Similarly, we have a chart here. Maybe we're sampling a bunch of students or over a variety of weeks, and we want to see how much time they slept on Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, and Sunday. Rather than just reporting an average or a median number of, say, 7.5 hours, I can see that this person on Monday nights, the low, they only got 4 hours of sleep. The high, they actually got 9 hours of sleep for Monday. So it gives me more information than I had before. All right, so let's take a look at this, guys. Use the data below on some quiz scores. See if you can find the mean, which is just the average, the min and the max. That should be pretty simple. The median, we want the middle value. And if there's two values in the middle, you want to average those two. The first and third quartile, so Q1 and Q3, go ahead and use the formulas that I had right here for Q1 and Q3, where it's going to be 0.25 times n plus 1 for Q1 and 0.75 times n plus 1 for Q3. The interquartile range, Q3 minus Q1, and the population standard deviation will be the real challenge problem. So you're going to need to find the average, the mean, subtract each of those from the mean, and then square them, add them up, divide by the number of entries, and take the square root and see what you come up with. All right, so there you go, guys. Lots for you to do, a lot of new